Okay, so here's another circuit where I've got two resistors, but let's notice one end of one resistor is connected to the one end of the one other resistor, but there is something coming out between them. Likewise, the other ends are connected and something is coming out from between there also. So these are not connected in series. This type of connection is called a parallel connection. So we've got a different kind of connection here. Let's take a look at how these things are related to each other. Now, again, we've got the high side of the power supply, so we're going to expect the current to come out this way, likewise to come in that way. The current goes up here, but notice we've got a branch point there. So we've got a current of I going in, but that current is going to split. And at this point, we don't know how much is going to go each way. So let's just call this, we'll call this current I1 and this one I2. So we've got three different currents we have to calculate. We don't know what any of these are. We're going to have to calculate what all three of them are. All right, now what do we know? From Kirchhoff's branch rule, the junction rule, we know we've got a current of I going in here. So we've got I going in. What goes in must come out. So how much is coming out? Well, we've got I1 coming out and I2 coming out. So we've got I1 plus I2. Okay, there we go. Now let's apply the loop rule. Let's start here. And let's go around the outer loop first. So coming here, we'll jump across the power supply. What do we have? A delta V, change in voltage of 12 volts. Come across here, go up here, jump across here. Again, we're going with the current, so this is going to be a voltage decrease. So we have Ri, 3 ohms times I1. It's a decrease. And then we come back to where we started, equals 0. Well, bring that over there, divide by 3 ohms. What do we have? I1 equals 12 volts over 3 ohms equals 12 over 3, 4 amps. So I1 is 4 amps. What about I2? Well, let's use the loop rule, go around the lower loop. So we'll start here. Again, jump across the battery, 12 volts. Come up here, jump across the 6 ohm resistor, minus Ri2, so minus 6 ohms I2. And that brings us back to where we started, equals 0. So bring that over there, divide by 6 ohms, and we have I2 equals 12 volts over 6 ohms equals 2 amps. So I1 is 4 amps, I2 is 6 amps, so they are different. What's the total current? Well, the total current is I1, 4 amps, amps, plus I2, which is 2 amps, which is 6 amps. In other words, the total current leaving the battery is 6 amps. There we go. Great. We figured out all the currents. I1 is 4 amps. I2 is 2 amps. And the total current I leaving the battery is 6 amps. All right, very, very good. Excellent. We looked at all those. Now, can we do a similar trick that we did with the series circuit? Can we replace these two resistors with a single resistor that would give rise to the same output for the power supply? That would give us the same voltage and total current. Well, let's try that. So, if we've got a 12 volt power supply putting out 6 amps, what resistor would we have in here? Well, again, V equals Ri. R will be equal to V over I, or 12 volts, over 6 amps. In other words, 2 ohms. So we can actually replace these two resistors, the 3 ohm and the 6 ohm, with a single resistor, a 2 ohm resistor, that would give rise to the same output for the voltage, the power supply, the same current from the power supply, as we did by having the two resistors. Again, that is called the equivalent resistance for two resistors in parallel. Now, for the series circuit, it was pretty easy to see 3 plus 2 equals 5. The sum is what we were looking at. But what about here? We've got a 3 and a 6. How do we get 2 ohms out of a 3 ohm and a 6 ohm? Well, again, let's try and do this in the general case with just some unknown voltage V and some unknown resistors R1 and R2, and let's see if we can calculate what the equivalent resistance is in that case. Okay, so here we've got the general case, a voltage V, putting out an output current I, a resistor R1 with a current I1, a resistor R2 with a current I2. Now, applying the branch rule, we've got, say, at that point, a current I going in, and a current I1, and a current I2 coming out, so I must equal I1 plus I2. Now you might say, well, what about this point over here? What about applying the branch rule at that point? Well, we could do that. What do we have going into that point? We have I1 going in and I2 going in, so we have I1 plus I2. What comes out? Well, I comes out, so we would have I1 plus I2 equals I. Well, but that's exactly what we've got up here. We're actually not getting any new information from that. So we only need to apply the branch rule one time in this case. The other branch point doesn't give us any additional information. All right, now what about the loop rule? So let's start down here again. Let's go around the outer loop. So coming across here, jumping across the power supply, a voltage increase of V. Then we come around the outer loop, jump across the R1 minus R1 I1. And that brings us back to where we started. That must equal 0. So let's bring that over there. Let's divide by R1. And what do we have? We have I1 equals V over R1. Okay, there we go. Now, let's rule around the outer loop. So coming down here, jumping across the power supply, we have V. And jumping, whoops, sorry, not up there, come down here, jump across R2, we have minus R2 I2. That brings us back to where we started, so this equals 0. Let's bring this over there, divide by R2, and we have I2 equals V over R2. Okay, there we go. Great. Now, again, what we want to do is try to replace these two resistors with a single resistor. So let's draw that new circuit with a single resistor in place of the two in parallel. Okay, so here is the new circuit with only a single resistor with the same voltage, same current coming out of the battery. But now we've only got one current in the entire circuit. So the current that comes out of the battery must be the current that's going through this equivalent resistor. So what do we have? Applying the loop rule, V, oops, sorry, I'm jumping ahead, V minus Ri equals 0. Or, bring it over, divide by R, I equals V over R. There we go. Now, let's take I1 and put it in here for I1, I2 and put it in here for I2, and I and put it in here for I. And what do we get? Well, we get I is V over R equals I1, which is V over R1, plus I2, which is V over R2. Well, we can divide off V from all of that, and what do we get? We get 1 over R is equal to 1 over R1 plus 1 over R2. The equivalent resistance of the two resistors in parallel we can find from this result here, the inverse of the equivalent resistance is equal to the sum of the inverses. In other words, 1 over R1 plus 1 over R2. And actually, you can imagine if you put in more resistors in here, R3, R4, R5, whatever, you could add in plus 1 over R3 plus 1 over R4 plus etc., etc. Now, this equivalent resistance for resistors in parallel, we will call R sub P. R sub P for resistors in parallel. So this would be R sub P, the equivalent resistance of resistors 2 or more in parallel, we find by finding the inverse of the resistance is equal to the sum of the inverses. Very, very good. Now, how does that compare with what we got from our previous problem? Well, in that case, we had a 3 ohm and a 6 ohm resistor. So what would we get for the equivalent resistance in that case? We would get 1 over Rp is equal to 1 over 3 ohms plus 1 over 6 ohms. Well, what's that? We've got 1 over 3 plus 1 over 6. 1 over 3 is 2 over 6. 2 over 6 plus 1 over 6, that's 3 over 6. So this would be 3 over 6 ohms. Well, dividing that out, that's 1 over 2 ohms. We have to take the inverse of that, so Rp is 2 ohms, and that is exactly what we found. The equivalent resistance for the 3 and the 6 were 2. So that seems to be exactly what we want. The equivalent resistance for 2 resistors in parallel, we find from the inverse of the equivalent resistance is equal to the sum of the inverses, or we can include more resistors if we've got more than just 2 that are in parallel. But remember, for resistors to be in parallel, both ends of the resistors, or all ends of, if there's more of them, so if we had, say, another one connected like this, or like this, so the ends, one end of all of them have to be connected, and the other end of all of them have to be connected, just like that. Okay? That makes them in parallel. Very, very good. Let's take a look at how much power is used by these circuits, a series and parallel. Okay, so here we've got a series circuit, and then the resistors in series replaced by the equivalent series resistance. And let's take a look at how much power these circuits use. Remember, the power used by a resistor, we can write either IV, I squared R, or V squared over R. Because we've got the resistances and the current for each resistor, we'll use I squared R. So the power used by 2 resistors will be the sum of the power used by each one. In other words, the total power will be P1 plus P2. The power used by the first resistor will be I squared R for this one. In other words, 3 amps squared times 3 ohms. And then the power used by the second resistor will be I squared R for that one. Same current, plus 3 amps squared times 2 ohms. Which gives us what? Well, 3 squared is 9, times 3 is 27, so this will be 27. And what are the units for power? An amp squared ohm, what's an amp squared ohm? Well, that's an SI unit, so what's the SI unit for power? A watt. So 27 watts, plus 3 squared is 9, times 2 is 18, plus 18 watts, again. And 27 plus 18 is what? 45 watts. There we go. So the total power used by these 2 resistors is 45 watts. Now, how much power would be used by the single resistor, the equivalent resistance? Well, the power will be I squared R, I squared 3 amps squared times 5 ohms. 3 squared is 9, 9 times 5 is 45. And we find it is exactly the same as the power used by the 2 individual resistors. So it really does seem that in terms of at least the response of the power supply, how much power is used by the circuit, replacing 2 resistors in series with the equivalent series resistance, in other words, the sum of the individual resistances, is exactly the same, gives us exactly the same circuit. Great, what about the parallel circuit? Okay, so here are the here's the parallel circuit with the resistors in parallel replaced by the equivalent resistance. Let's look at the power used in this case. Again, the power used by two resistors will just be the sum of the powers used by each one by themselves. So the power used by the first, again, I squared R. Now, the current in the 3 ohm is 4 amps. So the power used by the 3 ohm resistor will be 4 amps squared times 3 ohms, while the power used by the 6 ohm resistor, the current is 2 amps, so this will be 2 amps squared times 6 ohms. So what do we get? 4 squared is 16, times 3 is 48, so that's 48 watts, plus 2 squared is 4, 4 times 6 is 24, so plus 24 watts. And what do we have? 48 plus 24 is 72, so 72 watts. So the total power used by the two resistors in parallel, 72 watts. What do we get for the single resistor using the equivalent resistance from parallel? Well, we'll get, now using the current from the battery through the resistor, 6 amps, we'll get a power of I squared 6 amps squared times 2 ohms. And what's that? Well, 6 squared is 36. 36 times 2 is 72 watts. And again, that is exactly what we found from adding up the two powers. So again, it really seems that when we replace the equivalent resistance, we replace the resistors with the equivalent resistance, we do get a circuit that acts exactly like the original circuit. Okay, great. What about something even more complicated?